The massive earthquake that woke up Alaska.
2025 is shaping up to be a year when the ground beneath our feet and the oceans off our shores have never felt more unstable.
The Aleutian Subduction Zone, a formidable geological boundary stretching from the Gulf of Alaska deep into the Pacific Ocean, has long been recognized as a crucible of seismic activity. Recently, however, scientists monitoring this region have issued a red alert following the detection of highly unusual subterranean movements. These strange and intensified geophysical signals, captured through an extensive network of seismometers and GPS arrays, suggest a potentially significant shift in the behavior of tectonic forces beneath the Earth's crust. Unlike routine tremors or slow-slip events typically recorded along this volatile boundary, the latest readings have defied established patterns, sparking urgent concern among geophysicists and prompting emergency alerts across international monitoring agencies. Before we start, smash the like and subscribe buttons for more updates. At the heart of the issue lies a sudden and anomalous increase in deformation along a critical segment of the subduction interface. For days, instruments positioned along the Aleutian Arc have captured accelerated ground displacements, not only in frequency, but in the amplitude and character of the movements. These subtle but potent shifts are not the dramatic jolts of traditional earthquakes, but rather the kind of creeping, pressurized motions that signal massive strain accumulating silently over time. What makes this event particularly alarming is the speed with which these changes have emerged. Over the course of mere hours, the pressure buildup that would normally evolve over weeks or months has spiked precipitously. Beneath the surface, the Pacific Plate is thrusting itself beneath the North American Plate at a faster rate than expected, suggesting that the tectonic interface may be nearing a critical threshold. This zone, already a known producer of megathrust earthquakes and tsunami-generating events, appears to be priming for a potential rupture. Deep tremors that usually occur sporadically have begun clustering, coalescing into what seismologists call seismic swarms. These clusters often serve as prelude to larger seismic events, especially when occurring at intermediate depths within subducting slabs. The Aleutian region, known for its ability to release vast amounts of energy along segmented fault lines, seems to be transitioning into a new phase of tectonic behavior, one that could unleash significant geological consequences. What has puzzled experts is the geographic specificity and sheer energy intensity of the recent activity. The western Aleutians in particular have shown profound geodetic shifts, suggesting that the locked zone where the plates are coupled has begun to fail in discrete patches. This process, known as episodic tremor and slip, typically signals a slow release of pressure. However, in this case, the energy isn't dissipating evenly. Instead, stress appears to be transferring unevenly along the fault, piling up in adjacent locked segments and increasing the odds of a sudden break. The situation is made more volatile by the structure of the subduction zone itself, a jagged, deeply embedded fault complex that can trap and amplify tectonic energy in unpredictable ways. Increased magmatic intrusion has also been observed beneath several Aleutian volcanoes, most notably those near the eastern segments of the arc. Satellite thermal imaging and ground-based sensors have detected rising magma movement, suggesting a possible connection between tectonic unrest and volcanic systems. The subduction of oceanic crust into the mantle often introduces volatiles like water, which lower the melting point of the overlying mantle wedge, generating magma. When tectonic compression intensifies, this melting accelerates. This interconnectedness between seismic and volcanic phenomena is raising eyebrows among geologists who believe that a dual threat, a major earthquake followed by potential volcanic eruptions, cannot be ruled out. This pattern of deep earth disturbances has historical precedents. The Aleutians have been the site of some of the most violent seismic episodes in recorded history. The 1964 Alaska earthquake, one of the most powerful ever documented, unleashed a devastating tsunami and resulted in widespread destruction across the Pacific. While that event originated further east, it exemplified the catastrophic potential of sudden plate movement in this region. Today's signals bear eerie similarities to precursory patterns observed prior to previous megaquakes, including a combination of slow deformation, silent tremors, and the subsequent migration of seismic energy outward along the arc. Adding to the urgency is the lack of aftershock decay typically seen following seismic swarms. In most tectonic episodes, a main event is followed by a tapering series of smaller tremors as the crust settles. In this case, however, the seismic activity has sustained its pace without tapering off. The persistence of tremors, combined with subtle vertical uplifts along coastal monitoring stations, points to continued pressurization beneath the crust. It suggests that the fault has not yet released its full load of stored energy. Some scientists speculate that the zone may be entering a preparatory phase for a massive rupture, with each tremor acting like a microscopic fracture in a steadily cracking shell. One of the most unnerving aspects of this unfolding event is the unpredictability it introduces into earthquake forecasting models. Tectonic systems are complex, non-linear, and influenced by a multitude of poorly understood variables. The current Aleutian activity seems to defy conventional modeling predictions. Traditional algorithms that would normally calculate probabilities for large ruptures based on historic patterns and strain accumulation are failing to deliver coherent forecasts. As such, geophysicists are turning toward real-time machine learning tools to analyze the onslaught of incoming data, hoping to detect correlations between strain rate changes and tremor intensities that could offer a clearer picture of what's building beneath the surface. Even small changes in this zone can have disproportionately large impacts. The Aleutian Islands act as a geological bridge between the Pacific Rim and the Alaskan mainland, making them a crucial seismic gateway. A significant event here would not remain isolated. Its shockwaves, both literal and figurative, would ripple through the broader tectonic ecosystem of the Pacific Plate. Subduction zones don't function in isolation. When one segment destabilizes, it redistributes stress across adjacent zones, potentially triggering chain reactions. A rupture in the Aleutians could send stress toward the Cascadia Subduction Zone, or southward toward the Japan Trench, where seismic tension already simmers beneath the surface. Maritime routes that pass through the Bering Sea and into the Arctic are also at heightened risk. Undersea cables, essential for global internet infrastructure, thread through the oceanic depths near this active zone. A major earthquake could sever these lifelines, disrupting digital communications and financial systems across multiple continents. Oil and gas operations in offshore Alaskan territories could also be impacted, not just by ground movement but by secondary hazards such as undersea landslides and tsunami waves. The economic implications of a tectonic event in this region could be staggering, extending far beyond the immediate geophysical concerns. Meanwhile, coastal communities in Alaska and parts of northeastern Russia are ramping up their emergency readiness protocols. While no evacuation orders have yet been issued, the issuance of a red alert is a rare and serious move by geological authorities. It signifies not just the presence of ongoing tectonic activity, but a credible risk of escalation. Emergency services, public safety officials, and national disaster preparedness agencies are coordinating closely, running simulations and reinforcing infrastructure that might be exposed to seismic or tsunami impacts. Local populations are being urged to review evacuation routes and secure essential supplies in anticipation of a worst-case scenario. Beyond the realm of emergency management, the scientific community is responding with rapid deployment of new monitoring equipment. Drones outfitted with hyperspectral imaging and aerial LiDAR are being flown over the most active regions of the Ark. Deep-sea rovers are descending into submarine trenches to gather real-time data on hydrothermal venting and sediment shifts. These multidisciplinary efforts aim to create a more granular picture of tectonic interactions at a scale never before achieved. The goal is not only to predict immediate outcomes, but to understand how this particular subduction zone might behave differently from others under similar stress loads. What makes this all the more fascinating and alarming is the role that climate change may play in subtly influencing tectonic processes. While earthquakes are fundamentally driven by geophysical forces deep within the Earth, some researchers have proposed that melting glaciers and shifting oceanic loads can alter pressure dynamics on fault lines. The Aleutian region, with its complex interplay of ice, ocean, and crustal movement, may be experiencing new stresses due to these surface level changes. Isostatic rebound, the gradual lifting of land once compressed by glaciers, can reactivate dormant faults and destabilize previously locked zones. If this hypothesis holds merit, it may mean that external environmental changes are interacting with deep Earth systems in ways that science is only beginning to grasp. In addition to these tectonic interactions, biological systems along the Aleutian coastlines are also being closely watched. Whales and other marine mammals have reportedly altered their migratory paths in recent weeks, a phenomenon that some biologists correlate with changes in the Earth's magnetic field or with subsonic vibrations generated by deep Earth activity. These animals often detect frequencies below human hearing range and may serve as natural barometers for seismic stress. Fishermen have reported unusual behavior among deep-sea fish, many of which have surfaced unexpectedly, perhaps disoriented by pressure changes or underwater tremors. The convergence of so many indicators, seismic swarms, magmatic intrusions, ground deformation, and marine anomalies, paints a portrait of a system under siege from within. While it is impossible to determine with certainty whether these strange movements will culminate in a catastrophic earthquake, the signals are ominous and warrant heightened vigilance. Each passing hour of sustained tectonic motion without a pressure release increases the risk of a sudden and dramatic rupture. The window for potential energy release is not infinite, and once it closes, the outcome may be decided not by human prediction, but by geological inevitability. As scientists continue to dissect the torrent of data coming from the Aleutian Arc, there remains a palpable tension in the air, an awareness that the Earth beneath this region is stirring in ways that it hasn't in decades. Subduction zones are not static entities. They evolve, sometimes quietly, sometimes violently, and always with consequences. The red alert is not a proclamation of doom, but it is a recognition that something fundamental has changed beneath the surface. The Aleutian Subduction Zone, always formidable, has entered a phase of instability that may very well become one of the defining geological events of the century. As the red alert remains in place over the Aleutian Subduction Zone, attention has turned to the more intricate aspects of how tectonic energy behaves under extreme pressure scenarios. Seismologists now find themselves grappling with the challenge of interpreting the anomalies without the aid of precedent. What makes the current episode profoundly unusual is not merely the scale of the deformation or the velocity of tectonic creep, but the emergence of completely new seismic signatures, signals that do not conform to established earthquake waveforms. These hybrid tremors, as they are being referred to, exhibit a curious blend of low-frequency resonance and abrupt high-energy bursts. They are rare, poorly understood, and virtually unseen in this part of the Pacific Rim until now. Initial spectrogram analyses have shown that these hybrid tremors emanate from depths deeper than the majority of known Aleutian quakes. The implications are profound. At such depths, beyond 70 kilometers, the crust transitions into the upper mantle, where high-pressure minerals like olivine behave plastically rather than brittly. For seismic activity to occur in such ductile regions, extraordinary force is required. These unusual signals suggest that the entire subduction system may be experiencing torsion or shearing forces not normally observed in its geological history. Some researchers speculate that the slab itself could be undergoing internal deformation, a buckling, twisting motion that may precede a full structural reconfiguration deep within the mantle interface. Further complicating the situation is the unexpected lateral migration of seismic energy. Traditional plate theory assumes that subduction proceeds in a mostly vertical direction, with the oceanic plate plunging beneath the continental crust in a downward motion. However, the data streaming in from the Aleutian chain suggest a strange sideways slippage occurring along secondary faults that branch out from the main plate interface. This kind of lateral stress dispersion has the potential to activate dormant fault segments previously considered inactive or non-threatening. In other words, the tectonic disturbance may not be limited to a single fracture plane, but instead could set off a cascading failure of crustal blocks across a wide geographic area. Adding a new layer of concern is the appearance of microfracturing in areas not previously known for tectonic weakness. High-resolution interferometric radar imaging has revealed surface fractures, narrow, shallow tears in the Earth's surface, extending over several kilometers in parts of the western Aleutians. These fractures are not remnants of past earthquakes, but appear to be new stress-induced features forming in real time. Their orientation and spread indicate that the crust is under multidirectional stress. Rather than a single vector of force pushing in one direction, the rock appears to be caught in a complex tug-of-war between expanding and contracting forces. This stress chaos is the type of environment that often precedes complex multi-fault ruptures, some of the most destructive and least predictable seismic events known. The subduction zone itself is not a clean, continuous surface. It is serrated, irregular, and peppered with geological asperities, stuck zones where friction prevents movement until a threshold is reached. These asperities behave like geological pressure cookers, trapping energy that, when released, causes disproportionately large earthquakes relative to their size. Satellite imagery now shows that several of these asperities along the Aleutian front are starting to deform in irregular patterns. The deformation appears to be radiating outward, suggesting that stress is now working its way around these locked zones rather than being halted by them. This fluid redistribution of tectonic energy raises the possibility of a more widespread and simultaneous rupture scenario, something rarely considered but theoretically possible in zones as fragmented and stress-laden as the Aleutians. Ocean bottom seismometers deployed in an extensive grid across the Aleutian Trench have also begun recording harmonic tremors, continuous rhythmic ground vibrations often associated with the movement of magma or superheated fluids. What makes these tremors intriguing is their duration and spacing, typically lasting only minutes. Some of these recent tremors have endured for over an hour and occur at intervals that suggest a pressurized system venting in cycles. While these might be purely tectonic in origin, the harmonic nature implies a possible hydrothermal component. The subduction of water-rich oceanic crust generates enormous volumes of pressurized fluid deep underground. If these fluids are now being released in significant quantities, they may be lubricating the fault zone, increasing the risk of a slip event, or alternatively, fueling undersea volcanism. The presence of methane plumes rising from the seafloor further complicates the situation. Methane hydrate deposits, typically stable under immense pressure and low temperature, are beginning to destabilize in certain pockets along the slope of the trench. Undersea drones have captured footage of methane bubbles escaping through fissures and mud volcanoes, indicating thermal or tectonic disruption in the sediment layers. The destabilization of methane hydrates is both a geophysical and environmental hazard. Not only can it contribute to slope instability, potentially triggering underwater landslides and secondary tsunamis, but it also adds to the atmospheric greenhouse gas load if large volumes escape and reach the surface. This is a reminder that seismic activity in this zone can have far-reaching consequences beyond immediate ground shaking. These disturbances are being analyzed in parallel with magnetic field anomalies. Several monitoring stations along the Alaskan Peninsula and offshore islands have reported subtle but persistent changes in geomagnetic readings. These anomalies are not typical magnetic storms from solar interference. Rather, they seem to coincide with deep Earth tectonic shifts. As rocks under high pressure undergo deformation, they can generate piezomagnetic effects, small magnetic fields created by mechanical stress. The synchronized occurrence of magnetic and seismic fluctuations is leading researchers to consider whether deeper, perhaps even core mantle interactions, could be playing a role in what is unfolding. It may be that the Aleutian subduction system is not just responding to surface or crustal forces, but to something much more profound and far-reaching within the Earth's interior. This possibility gains further weight when considering the thermal flux anomalies emerging from deep boreholes used for geothermal monitoring. These sensors, buried kilometers below the surface, have detected sudden increases in temperature gradients, even in areas not associated with volcanic systems. This suggests that tectonic activity is generating heat faster than it can be conducted away, an indication of intense frictional strain or the movement of hot pressurized fluids. Thermal buildup in fault zones is a well-documented prelude to rupture. If the rocks are heating rapidly, it may signify that mechanical friction is nearing a critical threshold. Once that threshold is crossed, the accumulated strain could trigger a rupture event with explosive energy release. Meanwhile, strain meter data, collected from deep embedded sensors designed to detect even microscopic shifts in crustal compression, are reporting values well outside historical baselines. These instruments are measuring elastic deformation that continues to accumulate even in the absence of visible earthquakes. This so-called aseismic slip is troubling in its own right, because it masks the amount of strain that is not being released through normal seismic mechanisms. In other words, The Earth is bending and compressing without cracking, yet. But when it does, it may not be a gentle release. The longer the system holds together without giving way, the more energy it stores, and the more violent the eventual rupture is likely to be. If you liked this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on these Aleutian Subduction Zone movements scientists just detected? We want to hear from you. Thank you for watching and see you next time.